1991 Gulf War is remembered today as a moment in history when an international effort succeeded in removing the Iraqi dictator Saddam Hussein's forces from neighboring Kuwait. But this brief, decisive conflict has also come to be called the world's first space war. Orbiting the Earth, thousands of miles above the battlefield, were satellites, spacecraft with revolutionary technologies that were making their debut on the world stage. The Global Positioning System.
GPS was the unsung hero of the Gulf War without a doubt.
Yes, the air raid siren.
Communication satellites, beaming the events on the ground in real time to a global audience.
When satellites came in, oh my God, it changed the way journalism was done.
Slowly and steadily, the sky above us has become populated with spacecraft that today are the invisible infrastructure of our world. It is a revolution that began decades before, when the world first heard a faint signal broadcast from the edge of space. October 4th, 1957.
The world's press announces the miracle of the age. The Russians had successfully launched Sputnik, the first satellite ever to circle the Earth.
Despite the global fanfare, Sputnik's technology was primitive. A rudimentary sphere with a simple radio transmitter that beeped.
Sputnik just showed that you could put a man-made object into orbit, and it did that by just beeping, but it didn't provide anything else.
Harold Rosen was a young engineer at Hughes Aircraft in 1957. He immediately envisioned a far more useful satellite, one that would revolutionize the way the world communicated.
At that time, international communications was in very poor shape.
If you wanted to make a telephone call from one continent to another, you had to reserve the line. It was a physical wire that went underneath the ocean between two continents.
The call would be scratchy, and it would be a big formal event.
And as far as television was concerned, it was impossible. So a lot of people felt that this sad state of long-distance communications could be alleviated with a properly designed communication satellite. But what kind?
Engineers at AT&T were developing a vast network of as many as 120 satellites in orbit just a few thousand miles above the Earth.
It would require a massive network of antennas tracking these things and handing calls off back and forth. And Harold Rosen looked at this and said, this is not a very elegant way to operate a system.
Rosen found a possible answer in the futuristic speculation of science fiction writer Arthur C. Clarke. He imagined a satellite that would appear to stand still in the sky, as if hovering in one spot, a geostationary satellite.
But any satellite, in order for it to stay in orbit, has to itself be circling the Earth. So the trick then is, how do you get a satellite to both orbit the Earth but be in a fixed location?
The farther a satellite is from the surface of the Earth, the more time it takes to complete its orbit. A satellite placed into orbit 22,300 miles above the equator would take 1 day to circle the Earth.
The insight that Arthur Clarke had was that the Earth rotates once every 24 hours. So if you had a satellite that also completed its orbit once every 24 hours, it would seem to hang motionless over the equator.
So if you had 3 satellites in geostationary orbit, they could cover the whole Earth. But the technical problem was how to design a satellite that could get to geostationary orbit, stay there, and serve as a communications relay.
Nobody thought it could actually be done. What Harold saw was a way to do it.
Rosen recruited two fellow engineers at Hughes Aircraft, Tom Hudspeth and Don Williams, to help work on a design. But company executives were skeptical.
Most of the people I talked to thought it was pretty wild, and it was pretty wild. It was a difficult sell at Hughes.
In the 1950s, Hughes Aircraft was really just coming into its own as a scientific powerhouse. It was privately owned by this eccentric billionaire.
Hughes Aircraft had been founded in 1932 by Hollywood mogul and aviator Howard Hughes.
Whatever his eccentricities were, his great talent was getting good people that he knew would lead the charge on developing new things.
But Rosen's idea was a risky, expensive challenge, even for Hughes. His satellite would need to travel nearly 40 times farther into space than Sputnik.
Getting stuff into space requires a tremendous amount of energy. A critical part of making that happen was to create satellites that were light enough to get them up into geostationary orbit around the Earth.
Even if Rosen's satellite could get there, he had to figure out how to keep its antenna pointed at Earth.
When something's on the Earth in gravity, it's real easy to figure out which way it's going to stay pointed. The heavy end goes down. When you're out in space, it's really hard to keep things oriented in a particular direction.
Rosen's solution was both elegant and simple.
Like any normal kid growing up, Dr. Rosen would throw a football around, and he knew that if you threw a spiral pass, it would stably fly through the air because it would spin around its long axis. So he figured out a way to get a satellite spinning around its long axis. And as long as it was spinning, it would stay pointed exactly the right direction.
Rosen convinced Hughes to fund a prototype. It was dubbed SYNCOM, for synchronous communications.
It was a major investment for them at the time. It was $300,000. Took a lot of talking to get that.
But Rosen and his team still needed a big, rich sugar daddy to fund putting this thing into orbit.
In secret, the U.S. Defense Department had started to develop its own version of a geostationary satellite.
The federal program was in serious trouble. The prospective weight of the satellite was many, many hundreds of pounds. There were serious cost overruns.
Overseeing the Defense Department's program was a former Hughes executive, John Rubel.
Rubel went to Rosen's laboratory and he was awestruck. He took one look at it and he said it was the answer to all of our problems. So Rubel pulled some strings and figured out a way to allow NASA to help fund the project.
In August 1961, NASA awarded Hughes a contract for 3 SYNCOM satellites.
The first one, by the way, blew up. It was quite a disappointment, but we changed a bunch of things in a hurry, and a few months later, we were ready with SYNCOM 2.
SYNCOM 2 was successfully launched on a Thor Delta rocket built by Douglas Aircraft from Cape Canaveral on July 26, 1963.
This was the first time anybody had put an object into higher orbit, 22,000 miles into space. It was a crucial accomplishment to achieving, global communications.
In October 1964, SYNCOM 3 made history, beaming the first Olympic television transmission across the Pacific.
Seeing the opening ceremonies of the Tokyo Olympics, that was a terrific moment. I remember to this day the young man running down with the torch, lighting the flame. It just felt great.
Little SYNCOM was just the beginning.
SYNCOM 3 was capable of transmitting only one television signal at a time. A modern-day satellite can communicate 100 or more simultaneous television signals in high definition But what has remained the same is the concept that Harold Rosen developed in the early 60s.
It was so sweet a technological answer that virtually every communication satellite since then has been in geostationary orbit, all one way or another descendants of what Rosen and his team created.
Nearly 30 years after the launch of SYNCOM, Rosen's technology was poised to transform the Gulf War into a global television event, changing the way news would be reported forever.
That's the latest in a series of cruise missiles that have been flying into Baghdad over our heads.
In the early morning hours of August 2nd, 1990, Iraqi dictator Saddam Hussein sent his army into neighboring Kuwait and seized control of that country's oil fields. This act of brazen aggression was widely condemned around the world.
This will not stand, this aggression against Kuwait.
A massive coalition of 34 countries pledged to evict Saddam from Kuwait by force if he did not withdraw by January 15th, 1991.
It was the biggest international coalition since World War II. So the whole world felt it had a stake in what was going on. That made it a huge story.
News media descended on the region, armed with a new technology, portable satellite dishes.
Previously, there was really no way to provide live TV coverage from the front.
This great new science of satellite technology came of age during that first Gulf War. And it really enhanced the ability to bring people to an event.
And for us, it would be a huge test for a very young TV network.
CNN was a cable news upstart, founded just 10 years earlier by Ted Turner.
Ted Turner in the 80s had made a fusion of television and satellites. In the past, news was about what had happened. It had now become a situation where news was what was happening at that time.
CNN was the first 24-hour all-news channel, a challenge to the major networks ABC, CBS, and NBC.
Network news at that time was only 30 minutes a day.
Turner said, I believe that people want live news, and there's no reason they shouldn't have it anytime they want.
And it was only through satellite communications that that vision of his became possible.
CNN would use a network of satellites to beam live reports to viewers around the globe. The major networks broadcast only to America. On the eve of the Gulf War in 1991, more than 100 countries received CNN coverage, including Iraq.
Saddam Hussein and his henchmen in Iraq, they watched CNN. CNN was their network, and that became a great advantage.
President George H. Bush had promised that it would be the biggest airstrikes in the history of military if indeed Saddam did not pull out of Kuwait. The deadline passed on January 15.
At 3 a.m. Baghdad time on January 17th, the airstrikes began.
The first bomb to fall was to sever the communications links in what we call the AT&T building, their telephone network building.
To get their reporting out, the major networks were relying on phone lines in the telecommunications building.
So I sent a major from my staff up to where there was a television set, and I said, let me know what happens.
And sure enough, at the exact minute, the television broadcast just went dead.
Whoa, holy cow. That was a large airburst that we saw. And I think, John, that airburst took out the telecommunications.
All the networks went dead, except CNN.
If you're still with us, you're going to hear the bombs now. They are hitting the center of this city.
Saddam had allowed CNN to establish a private audio connection to a bureau in Amman, Jordan.
Satellite technology brought that audio signal from Jordan back to the United States, and from the U.S. we were able to transmit that globally.
The skies over Baghdad have been illuminated. We're seeing bright bright flashes going off all over the sky. Peter?
We were not sure about whether or not we'd survive the night, to tell you the honest truth. But the opportunity to actually talk about what we were seeing was unique.
There were loud explosions.
We were telling a story not just to America, but to the entire world.
Within several hours, the actual photos of pictures of what was going on were broadcast.
Tens of millions of viewers tuned in to CNN's coverage that was being beamed around the world by satellite.
To be able to see the American bombardment, it was pretty extraordinary. You know, Vietnam, film got shipped to Tokyo, Hong Kong, back to New York. It was days before you saw anything. This wasn't days, this was now.
It's one of those real amazing moments in the history of journalism where everything changed in a minute.
We knew what we were doing was unprecedented. Unquestionably, it really led to sort of an epic shift in the way in which news was covered and the way in which news was consumed. And we knew that we were a part of a much larger satellite technology equation that was really, in many ways, changing the world.
Communication satellite technology was delivering the war in real time for all to see. But there was another satellite technology whose role was far less visible. The Global Positioning System, GPS, was about to reveal its power to transform how war would be waged. The 1991 Gulf War marked the first large-scale use of precision weapons.
We are seeing examples of surgical bombing.
To veteran reporters like CNN's Peter Arnett, it looked very different from previous wars.
During the Vietnam War, there was a major problem with bombing targets, and tonight every bomb we've seen land seemed to have hit something.
We could see the palaces go down, communication centers go down, the Defense Department, the Defense Ministry going down.
Peter Arnett, in 1991 in Baghdad, saw what was unfolding around him. That, you know, these people weren't indiscriminately using weapons. They were using weapons very, very precisely.
Among these weapons was a new technology that was making its combat debut in a top-secret mission. 35 cruise missiles were released more than 100 miles outside Iraqi airspace. They were navigating on their own, guiding themselves to their targets.
These were GPS-guided weapons, the first GPS-guided weapons, and we used them against very specific targets for very specific purposes, and they were very effective.
For one man, it was the culmination of years of effort. Colonel Brad Parkinson had devoted his career in the Air Force to developing the Global Positioning System, GPS.
I felt that was vindication. And I guess my question would be, why did it take so long?
In 1969, Parkinson was on the faculty of the U.S. Air Force Academy when he was sent to Vietnam.
In Vietnam, the technology for precision weapon delivery was just beginning. Bombs rarely hit what they were aiming for. If you're trying to take out a bridge, you kept trying to take out the bridge, but you didn't have the precision weapons to do it.
There are many, many occasions when there were civilian casualties because of the difficulty of hitting targets. And so much of this enormous use of firepower was wasted or landed on others than intended.
By the end of the war, more than 7 million tons of bombs have been dropped on Vietnam and neighboring countries. More than twice the amount of bombs dropped on Europe and Asia in World War II.
It was a desperate war, it's an unfortunate war, and it's easy in hindsight to condemn that, but it was all we had.
Parkinson was really dismayed by how indiscriminate the bombing campaign was in Vietnam. The way he saw it, if you could come up with a way to drop bombs exactly where you wanted them to go, then that could transform warfare.
Parkinson returned with a mission, but no clear path to achieving it. The Air Force reassigned him to a top-secret program on satellite navigation.
I kind of got dragged in because of my background in navigation, and this particular program looked like it was going to be a loser. Congress didn't want to fund it, and it looked like a desperate cause.
Satellite navigation was invented by the Navy for its nuclear submarines, but their system was slow and unreliable. Now, both the Navy and the Air Force were pushing different ideas for a new and improved satellite navigation system.
Conflict between these two programs was somewhat inevitable because at some point the military would have to choose one or the other.
There was intense competition. The result was a sumo wrestle in which no one could fall down and no one could win.
The Air Force program's early design testing had proved their system could calculate position in fractions of a second with pinpoint accuracy. Parkinson had a realization. If a satellite system could guide a ship or an aircraft to a precise point on the surface of the Earth, why couldn't it guide a bomb to its target?
It was clear to me that this had the capability to be a generalized precision weapon delivery system.
For Brad, it was a way to try to, right some of the wrongs of Vietnam and the way that the air campaigns were fought there. It was a real revelation for him.
Parkinson was determined that the Air Force system would prevail, but the Pentagon had other ideas.
When I failed in August 1973 to get approval for what was solely the Air Force concept, I thought my promising career was probably over.
The Department of Defense stipulated that there would be a joint program to take the best of the ideas from the Navy and Air Force programs and combine them into one grand system.
They came to me and said, "You're the right person. Bring me a concept that's the best you possibly can. Use ideas from anywhere, the Navy, Air Force, unrestricted."
In late 1973, Parkinson got Pentagon approval to begin work on the Navstar Global Positioning System, what we know today as GPS.
I invented a motto that attempted to ensure we all were on exactly the same page, on the ultimate purpose. And the motto was the following: the goal of this program office is to drop 5 bombs in the same hole, and don't you forget it.
Make satellites do the work of guiding an object through space and time with such precision that every one would hit its target. GPS was invented to do just that. In 1974, at the Air Force Space and Missile Systems Organization, Colonel Brad Parkinson and his team were pushing the limits of scientific and engineering knowledge. The satellite navigation system they were designing would be made up of 24 satellites orbiting the Earth 12,000 miles out in space.
The concept was that the satellites are always moving in this constant sort of ballet, and they're arrayed in such a way so that pretty much every spot on Earth is always within a direct line of sight to at least 4 of them.
Each of the satellites would be constantly broadcasting a radio signal traveling at the speed of light, which could be picked up by GPS receivers on Earth.
Now, because the signal is traveling at a constant speed, at the speed of light, by knowing how long it's taken to get from the satellite to us, we can figure out how far we are from that satellite.
By measuring your distance from multiple satellites, you can determine your location. How this works can best be explained in 2 dimensions. Imagine you are trying to find your location on this map. You know you are 1,000 miles from point A, but you could be 1,000 miles in any direction, anywhere on this circle. You also know that you are 1,200 miles from point B and 800 miles from point C. Those circles intersect at just one point, your precise location. Now imagine those points on a map as satellites in space. If you know your distance from 3 satellites, you can determine your location. A 4th satellite determines altitude and improves accuracy.
With those 4 signals, using some fancy software, your GPS receiver can then figure out where it is on the surface of the Earth.
But the satellites and the receivers must be calibrated to the same clock. Time is at the core of GPS.
We need to know exactly the time it is when the signal left the satellite, and we need to know exactly the time it is when it reaches us.
GPS is the clock, and the clock is GPS. Without the clock, you get nothing.
Hugo Fruhoff was the chief engineer for Rockwell International, the aerospace contractor building the GPS satellites for the Air Force. Each of the satellites would need an atomic clock, a clock that measures time in billionths of a second. That level of precision was critical to making GPS work.
If you have clocks that don't know the time to, say, 10 nanoseconds, you're off by 10 feet.
The challenge facing Rockwell and the GPS program was how to put an atomic clock on a satellite and get it to work 12,000 miles out in space.
You don't take these devices, or you didn't in 1972, and put them up into space. Why?
You have to do a lot of things to survive radiation. So if you started with a 50-pound unit size of a microwave, and then you make radiation hardening, you end up with a 100-pound or so clock. And we need at least 2 or 3 for each satellite for redundancy.
But a stroke of luck and language delivered Hugo Fruhoff and Rockwell a solution.
During the exact time I was looking for a clock, one of my engineers said there's a guy out of Germany, he says he's got this small clock, but I just didn't believe it. It was just too good to be true.
In 1971, Ernst Jeckert left Germany and moved to Southern California. He set up a small company called Efratom to market his invention, a miniature atomic clock.
He built a unit that was 4 by 4 by 4 inches, weighed 3 pounds. Now, compare that to what I just said, about a 100-pound clock. His clock was revolutionary.
Efratom's clock was absolutely state-of-the-art, fabulous, but it was being built by Germans. One of the key engineers didn't even speak English at all. Well, Hugo was a native German speaker. Hugo's ability to cut through any communication problems was one of the keys.
But it was more than language difficulties that threatened the program.
Ernst was not a citizen of the United States. Remember, GPS wasn't designed for your car. It was a military system.
I guess he came on a visitor's visa, and midway they were threatening to deport him.
That would have been a disaster.
I had to write a letter saying, hey, it's critical to the national security, this program will fall apart if we don't keep some of this technology here in this country. And it worked.
That made him a legal American citizen. And so we built an entire clock, fully radiation hardened, ready to put on a satellite.
In 1978, 4 Rockwell GPS satellites were launched into space. Parkinson and his colleagues prepared to test the system.
The test program, in my view, from the beginning, was an absolutely essential leg, because frankly, there were a lot of doubters.
GPS was despised by a lot of the Air Force. I mean, you know, to the extent that people just weren't bored by it, they despised it.
You gotta remember, who's running the military? Where did they come from? They came from World War II. They came from Korea. So their idea was massive retaliation. It wasn't precision bombing. Why would you save the lives of the enemy? And the cost. The cost of GPS was so outlandish.
Parkinson's program was on track to exceed estimated costs by almost $2.5 billion.
One day, I was walking through the Pentagon, and I see a certain major general who I know is in charge of this money. He immediately wheeled up to my face, and he outranks me a lot, and he's saying, Parkinson, your otherwise illustrious career is about to go right down the tubes unless you stop advocating this program. You know, I kind of cringed. I looked him in the eye. I said, yes, sir.
Brad didn't really care about what a lot of his superiors thought of him. He just had this vision, and that was really the driving force behind this. Drop 5 bombs in the same hole.
Parkinson selected an Army facility in the Arizona desert to test the system. Large orange X's were placed across the desert floor, along with nearby seats for the doubters.
And we went off and blind bomb, dropped 5 blind bombs on that.
And lo and behold, it worked better than anybody expected.
They only saw 4 holes and discovered that one bomb had followed the other into exactly the same hole. So we did drop 5 in the same hole. Well, at least 2.
The success should have been greeted with enthusiasm, but it was not.
People at the time really couldn't foresee what precision location would really mean for the U.S. military and how that would contribute to transforming armed conflict.
That lesson would be learned with the whole world watching as coalition troops prepared to battle the ground forces of Saddam Hussein in the closing hours of the Gulf War. In February 1991, after a punishing 5-week aerial bombardment, Gulf War generals were preparing to send ground forces into Iraq. Saddam was expecting his forces to be attacked from the sea and from over the border in Saudi Arabia.
The Iraqi army had gotten pretty heavily dug in all across southern Kuwait and Iraq. And so a ground campaign to move them out could have been a multi-month affair with fairly heavy casualties on the ground. What was needed was an alternative strategy.
General Schwarzkopf, the Joint Task Force commander, came up with a plan to do an enormous sidestep maneuver to avoid a direct assault into Kuwait.
Dubbed the Left Hook, it would start the ground war and attempt the first large-scale, deep desert advance in the history of warfare.
No one had ever invaded Iraq from the middle of the desert. There were trackless sands. One would get lost very quickly.
For the Iraqis, the only thing that could reliably cross this desert landscape were camels and camel trains. The notion that you could have hundreds of tanks going through at high speed in a coordinated fashion during night and day was just unimaginable to the Iraqis.
What Saddam and the Iraqis didn't know is that coalition troops had a new tool in their arsenal, GPS. In addition to its use for precision bombing, GPS had always been a tool for determining location. When Colonel Gaylord Green took over the GPS program in the 1980s, he spent years urging the military to embrace GPS for ground navigation.
In the beginning, people would ask, what does it do? And I said, well, it tells you where you are. And they would look at me and say, I know where I am. I don't need a satellite system to tell me where I am. And I say, well, you don't really know where you are.
Saddam Hussein invaded Kuwait, and all of a sudden people started to realize how useful GPS could be.
But in 1991, the GPS constellation was not yet fully operational. Only 16 working satellites were in orbit, and the system called for 24. By repositioning satellites over the Gulf, they were able to get the coverage they needed.
But because GPS was not recognized before the war as being essentially a war-winning technology, very few receiver sets were actually available.
The few sets the military did have were distributed among troops as they waited to invade. At 4 a.m. on February 24th, the ground assault began.
Our maps looked like wallpaper. They had no detail on them. They just had latitude and longitude lines on them. So if you had one GPS receiver and, say, a whole company of tanks, that guy is the one they protected because he could tell them where they were.
GPS, along with night vision technology, allowed forces to advance day and night with unprecedented speed.
They could just barnstorm across the desert And that really took the Iraqi army by surprise.
The ground war lasted just 100 hours. On February 28th, Kuwait was liberated.
The Iraqis, when they were negotiating the peace treaty, told the Americans they never go out there because they always get lost. How did you do that? And one of the generals held up a GPS receiver there to show this is how we did it.
An incredibly large multinational armored formation was able to operate across what was perceived by the enemy to be a trackless desert and execute a strike that was one of the greatest maneuvers, I think, in the history of land warfare.
It takes a war some time to cement a concept or clarify its utility.
For Brad Parkinson, who staked his military career on bringing GPS to fruition, it was vindication.
The combination of precision bombing and emerging out of the desert at exactly where they thought they were coming out. It was kind of, yeah, now we get it. Now we get it.
It took nearly 20 years and a global conflict for the military to appreciate the power of GPS. The civilian world would grasp its potential much more quickly. In the shadow of the Rocky Mountains, there is a small, nondescript Air Force base with no runway. It houses what may be the military's best-kept open secret.
Most of the public doesn't realize that the central brain for GPS is out east of Colorado Springs at Schriever Air Force Base.
All day, every day, Schriever's 2nd Space Operations Squadron painstakingly monitors and manages the 32 GPS satellites currently orbiting the Earth.
Generally, at any one time, there are a handful of 5 or 6 airmen, average age of about 21, who are running the entire global GPS constellation.
But they are absolutely the most well-equipped and best-trained space professionals that we have.
Checklist 1-8, 4 go.
The satellites have to be supervised to an incredibly precise degree.
Are the batteries in the proper voltage? Is the clock running correctly?
Elevation is 38.4.
Essentially, they're watching to make sure that all of the parameters in the vehicles are within tolerances. Think of it as like a dashboard on a car.
So you have people shepherding or owning each satellite in a sense 24 hours a day, and without that, the satellites really wouldn't function.
There is no room for error.
Virtually every weapon system in all 3 services depends on GPS.
There are warfighters in harm's way whose lives depend on that signal.
But today, GPS is much more than a military system. Billions of people around the globe rely on the satellites controlled by these young airmen.
That's one of the most amazing things about GPS. It's owned by the Pentagon and the federal government of the United States, and it's controlled day to day by the Air Force. But every country, everywhere, and everybody uses it. It's the world's only free global utility.
And increasingly, that utility comes from its atomic clock.
One of the true innovations that GPS brought about was the ability to have a single synchronized timing signal available to everyone around the world.
In this age of electronics, where computers run at super speeds, a global timing system accurate to a billionth of a second is invaluable.
The timing signal we provide is so incredibly important. It times the world's economy. Everything the banking system does relies on that timing.
Wall Street. Sometimes the stock price can fluctuate tremendously in a fraction of a second, and you have to be able to prove that you bought the stock at a certain time.
GPS synchronizes the handoff of phone calls between the different cell phone towers.
Controls our stoplights.
Helps regulate our electrical grid.
The internet is timed off of GPS.
And that's above and beyond all the ways it's helping, the transportation infrastructure. It's guiding all aircraft. It's guiding ships and also guiding cargo when it's on the docks.
all because we've made the signal available and set the standard so that a user or a developer can take that and run with it.
Developers are finding applications for GPS that no one had ever imagined.
It's become almost indispensable in growing the world's food. Whatever you ate today, there's probably a pretty good chance that it was grown with the help of GPS.
On the tractor, on the top, there's a dome, which means they're using GPS.
It's known as precision agriculture, and it's become a multi-billion-dollar industry.
If you know exactly where you place the seed, exactly where to put fertilizer and water, and you know exactly where those things are, so when you harvest it, you pick up the crop right where it should be picked up, the efficiency adds up.
So instead of precision bombing, you can do precision pesticides, you can do precision fertilizing.
It's saving us runoff, it's saving us money, it's making food cheaper.
There's almost no aspect of our lives right now that aren't touched by GPS. It's almost like trying to measure the economic impact of electricity at this point. I mean, how would you even start to do that?
We knew it was going to be big, but we didn't realize it was going to be as big as it is. You know, every time I turn around, I see another application that, wow, I never thought of that.
Engineers and scientists continue to push the limits of technology to build ever more flexible, capable satellites with the potential to further impact human life. Today, the global satellite industry is a $208 billion business, but that relatively small number belies how rapidly our dependence on satellite technology continues to expand.
I don't think most people have a clue how much our lives depend on these things.
We couldn't fight the war without the use of satellites. News is instantaneous. We can see what's going on the other side of the world as it happens. We can conduct business on a global basis.
We are all on Earth wrapped up by satellites. Doesn't matter where you are, you're connected.
We could not have modern civilized life as we know it without the use of satellites today. And that's, I think, a remarkable change in human life.